difference. I will be probably a little bit out of the main topic because my talk will be more about the tree physiology than the other aspects. Let's start with the tree and the variables we can measure on this, and a little bit about function. So, yes, principally there is a soil, tree, and the environment, of course, atmosphere. One of the main important variable is the set flow, which is passing from the soil to the ground. And the set flow is driven by the differences between the relief water potential and the soil water potential. Soil water potential is somehow related through the PF curve with the soil water content, and the set flow is limited by the resistance of the conductive pathways. In the crown, the set flow is somehow transformed to the transpiration according to the leaf area. Leaf area is strictly related to the leaf area index, and of course the limited factor for transpiration is stomata conductance. Stomata conductance influence the difference between the potential evapotranspiration and the real transpiration. And on the other hand, stomata closure are influenced by other variables like soil water content and ambient factors, meteorological factors. The question is what we can measure, what we can really measure on this complex system. Of course, we can measure the leaf temperature, which is related to the difference between the potential evapotranspiration and transpiration. We can measure the set flow, which is now relatively easy. We can measure the stem shrinkage, because this is directly related to the xylem water potential, which is something between the soil and leaf water potential. No. This is another scheme which is probably too complicated for my original background is engineering. For me it's clear, but I'm not going to disturb you with this. But the only which is interesting here are two feedback loops. First with how the leaf water potential influence the stomata conductance, resistance in that case, and the feedback between the set flow and the leaf water content. So, a few notes, because I'm a little bit off topic, I will try to be very fast at least. Notes to this mentioned variables. Some of them are easily measurable, like soil water status, matrix potential, and volumetric water content is easy. Leaf temperature using the infrared sensors is also quite easy. Set flow, for this we have many different kind of sensor for the measurement of set flow. And of course, still the last one, which is efficiently measured, is the stem diameter changes in or shrinkage. Directly, the values which are directly calculated from the measured values are potential evapotranspiration, water pressure deficit, more or less, and then there are still some variables which are not so easy to calculate, which is a transpiration, which is mostly expressed as a canopy value, and stomata conductance, which must be calculated from potential evapotranspiration and set flow according to the parameterization of Bellman-Montes equation. There are also some parameters which should be taken into account, which are individual to each tree: leaf area, stem diameter, tree height, canopy parameters. All those parameters are necessary, for instance, for the calculation of stomata conductance according to Bellman-Montes and so on. Well, From all those values, which regards to the plant, to the tree, the easiest is to measure the stem diameter. Stem diameter changes. It's really very easy to measure, and it composes both most important variables, which is growth and drought. Growth it's clear. It's related to the water use efficiency and so on. And the drought is also especially now when the soil water availability is more often limited. This picture shows the real data of oak, of the annual curve of oak. On this axis it's simply the time, it's a growing season. These are the millimeters. And you see that probably you know that the growing curve should be like this, should be quite smooth. And in this area, which is marked with the blue color, are somehow limited. There are some negative differentiations, and next the positive one. And finally, after the heavy rain, it gets up to expected value. This is about the what we can read from this curves. So to list a little bit about the sensor for the measuring of stem diameter, stem shrinkage. We can start from the manual dendrometric. This one or that one, the other type of dendrometer which uses the frame for fixing, and it measures the real diameter between 2 points. This one which is point dendrometer, fixed with a screw here, and this is the measuring part. Or is also this point dendrometer, or this one which is the bend one which uses the whole diameter for the measurement. No, there are many discussions about the measuring with point dendrometers and with the bend dendrometers, but principally all of them are usable. It depends on the accuracy and stability of what you need. As for I should also say something about the data availability, because of course those manuals you have to read by eye. Some of them like these two samples has a built-in data logger with the data for I don't know exactly this one, but this one has a space for about 3 years of measurement. Also the battery inside is okay for 3 years. This is very shortly about the sensors. And what we need, or which specification of sensor are important, you can read here. Of course, first of all, is long-term stability, because the shortest time interval which we measure is one growing season, and the longest one is more or less infinity. So the long-term stability is quite important. Simply the dendrometer shouldn't influence the growth, shouldn't influence the tree behavior. It's always the problem with the measurement on living plants, that you can use many of sensors, many of complicated sensors with a lot of touching parts. You can get perfect results. On the other hand, it's a question if it is still the tree what you are measuring. So this is the good sensor is always the optimum between the accuracy and the influencing of the environment and the plant you are measuring. The durability is clear. Fix the position of the trunk. It's everything the same. The sensor shouldn't influence the tree, but on the other hand, it should fix very well on the bark. Good sensor has also good adaptability to different stem diameters. That means that it's for nothing if you have only sensor which is able to take 10 millimeters on few millimeters if the annual growth is 2 centimeters. So it's also a kind of criteria for selection of good sensor. Invasive installation, it's also the same. It's still the same story. If you screw down some part of some fixing frame, it always makes some response in growth. There is sometimes you see the callus. Sometimes it's simply you have to take into account the response of the tree growth on the sensors. The other point for point dendrometers is how to scale up the information from dendrometer to the whole circumference. If we suppose that the tree is growing, the radial growth is the same along the circumference is easy. If it is not true, it's probably recommendable to use the dendrometers the bent type dendrometers which simply measure the changes of circumference. And the last topic which is quite often discussed is the temperature dependency. There are a lot of experiments, lot of even papers which concerning this temperature dependency. In another word, the error which is caused by the changes of ambient temperature. It's of course it's caused. It depends on the design of the sensor, of course, on the material which are used. But it's very hard to distinguish which is really temperature difference and what are the real changes of the stem, because it's not only let's say the band of the sensor responds to the temperature, but also the tree trunk. It's not true that this if you see some oscillation, daily oscillation. It's only question of it's not caused only by the sensor, but also by changes by changes of the stem with the temperature. We have plenty of experience because we are fighting with this problem since 2010. And finally, our final decision is that it looks strange, but it really looks like the thermal expansion of the stainless, especially certain kind of stainless, is more or less the same like the changes of temperature. Because we know very well how is the temperature difference of the sensor together with the tape and with everything. But if you so it's relatively easy to make a correction. But in all cases, when we applied the correction, the temperature changes was more pronounced than without the correction. So finally, we suppose that the measurement without dendrometers, with dendrometers are more or less independent on the temperature, ambient temperature changes, just because both the tree and the sensor responds the same way. No, something about data processing. The analysis of annual curve is usually made with the help of some kind of theoretical ideal curve, mostly, at least in the forestry, it's mostly the bone pads. Some people use the sigmoid logistic curve, so, but mainly the bone pads equation. And then the analysis. So this is one point is to analyze one curve. The part of how to estimate the part of season when the tree was growing under the water stress and so on. So it's a detailed analysis, which usually use this comparison between the bone pads and the curve and the real annual curve, measuring annual curve. Another possibility or other approach is the mass analysis of many records of annual growth in order to get a comparison between the different species, different trees growing in let's say in a different size, in the different altitude and so on. So in that case, would be great if we know some important parameters which are listed here. So when the growth start, will end, what was the date of the maximum growth, maximum increment, the value of maximum increment, and the standard error of estimation of parameter of fitting curve, which I will explain later. So the first problem, the first approach, analysis of water stress. We see that this is the compared curve, the blue one curve is the compared curve, which is simply fitted to the annual curve. And so we can easily see the difference between the theoretical growth and the real measured values in that area, in this time period, which is mostly around August. So the question is how to calculate amount of missing water or and so on. But there is another problem because this situation, insufficiency of growth of the change, the smaller diameter simply combines both. Could combine both the tension due to very high silent water potential. That means when there is no water, the lead water potential must be still a little bit lower than the soil one in order to get water up. So the shrinkage is more, the daily oscillation, especially the daily oscillation, are mostly caused by the changes of let's say water potential. But there should be also discussed what happens when there is not enough water, when the tree couldn't get as many water as he would like to have. Therefore, probably the stomata are closer, and also the stomata as a gate for CO2 are also a little bit closer. Therefore, one could expect that in this time period was also the growth reduced. Who knows? The other approach is to analyze a lot of trees, a lot of daily curves, because there is really around the globe a lot of dendrometers on different tree species and so on, and we should find a method how to explain the differences between them. And during our attempts, we found that the compared curve doesn't fit very well to each situation, to all situations, as I will show you later. So after a lot of attempts, we found that instead of smooth curve, we can use something which we call broken line, which composed with two horizontal lines and a simple logistic pair, which has some advantage. First of all, we can exactly define the beginning and the end of growth, and we can adapt, the curve could be adapted for normal, let's say for a relatively normal shape of the annual curve, but also for this one when this the growth started very slowly, but it stopped suddenly in the late autumn. So it allows the vertical asymmetry. On the other hand, these sharp transitions are sometimes a little problem with analysis. Okay, let's go on. How it looks now, we will try to compare those approaches. The upper one is what I have already shown you. So this is the Gumpler scale with the nice pronounced time period of water stress, and the lower one looks absolutely the same, looks more or less the same, but instead of Gumper's is used this broken line curve. So you see that here is the one broken point, and this is the other one, and those are parameters analyzed from the curve. So you can exactly calculate all these 5 important parameters which can be used for describing of growth of different species in different sites of situation. So, and on the end, just a few samples. This one are annual curve describing the fitting with the growth in the years between 2006 and 14. You see how this is the beach, which from all trees I have ever measured have very smooth annual curves. You can see how big are differences in the shape of this annual curve in 8 years. So some of them looks very nice, like for Gumpert. Some of them are totally different. Like this one is more or less like combined from 3 lines instead of curves. Just to explain, there are the black points behind the blue one. Blue one are calculated, black points are measured values. So the fitting is okay. Probably it's one would say that there are not any big differences between the smooth fitting curve and the real measurement. Spruce, which was measured on the same place, the same years, shows totally different, a little bit simply different situation. There are in this year there are such a part of strong water stress probably, but it seems that some kind of water stress is appears in all years, especially this one, which was quite dry, and I think also this one. But still this. So there is an idea if we can use this standard error of estimation of the annual curve used for the establishing something like index of vulnerability to water insufficiency, which should be that the limited water supply is much more important for spruce than for beech, probably because of deeper, more shallow root system and so on. But what is the worst? The worst species in the point of view is larch. You see that there is only 1 year, this one or those 2 years, which are more or less similar to the fitted smooth line, and they are probably more vulnerable to the water stress in all a little bit dry years. On the end, these are the values of standard error of annual growth ratio by analyzed species. That means is how big differs this calculated curve from the reality. So beach is more or less has this. Take all the graphs have the same scale. So you see that the beech is relatively close to the fitting curve. The spruce has a problem, shows the problem in those years, and the larch is still the worst one. So it's a question of if we can probably this curve is not based on the physiological base principle. On the other hand, it fits for more situation, for more type of curves, and it's a question if we can use it for the processing, because it's for the processing of huge amount of annual curve measured with a different kind of dendrometers. Well, no, that's it. By the way, this curve, the equation which is used for the fit, this one is relatively complicated, and the process, the parameters are found with the iteration process, and everything was made in our Kucera software, which has a special module for non-linear multi-regression calculation. So the last note, would it be a method how to compare the vulnerability to stress of different species, different individuals. That's it. Thanks for your attention.